Hello everyone, in this video I am going to explain applications of inductive effect. This is important topic, applications of inductive effect, which explains stability of reaction intermediates like carbocation, carbanion, carbon free radical. It also useful to predict acidic strength of organic acids and basic strength of amines. In all these areas, inductive effect is very important. Directly, indirectly, it is the most important concept in organic chemistry. So first application is it explains stability of carbocation. Inductive effect explains stability of carbocation. What is carbocation? The species in which carbon carrying positive charge is carbocation. So the stability of carbocation explained by inductive effect. Stability of carbocation is directly proportional to plus I effect, inversely proportional to minus I effect. As plus I effect increases, carbocation stability increases. Example, if you see example, taking tertiary carbocation, carbon carrying positive charge. Next, secondary carbocation, primary carbocation taking ethyl carbocation, and simple methyl carbocation, super primary carbocation. If you compare these, here methyl groups are what? Methyl groups are CH3 group is plus I group. CH3 group is plus I group. Plus I groups are also called as plus I groups are also called as electron donating groups. Electron donating groups, shortly EDG, or electron releasing group. Plus I groups are also called as electron donating groups or electron releasing groups. So how is stability? Suppose this is A, this is B molecule, this is C species, this is D species, 4 species, not molecule, they are ions. Which one is stable? A more stable than B, more stable than C, more stable than D. So which one is more stable? A more stable than B, more stable than C, more stable than D. Because this is the tertiary carbocation in which how many electron donating groups are there? 3 electron donating groups are there. Carbocation is electron deficient. Electron donating groups stabilize carbocation. They push electron towards carbon, then carbon becomes stable. The magnitude of positive charge decreases, then carbon becomes stable. Here such electron donating groups are only 2 here. Here electron donating group is only 1 here. Here no such electron donating group. Hydrogen plus I effect is 0. Methyl group is plus I effect group or electron donating group. Electron donating groups increases, plus I effect increases, stability of carbocation increases. Here 3 plus I effects, here 2 plus I effects, here only 1 plus I effect, here 0 plus I effect. That's why which is stable? Tertiary carbocation is stable than, therefore carbocation stability is tertiary carbocations more stable than, secondary carbocations more stable than, primary carbocations more stable than simple methyl carbocation. Okay, hope you understood. This is very important concept. Here 3 plus I effects, 3 plus I groups, here only 2 plus I groups, here only 1 plus I group, here no plus I group. Thus stability of tertiary, secondary, primary and super primary, methyl carbocation super primary explained by inductive effect. Take this one. Second application, it explains stability of, inductive effect explains stability of carbene ions. What is carbene ion? The species in which carbon carrying negative charge. Okay. Stability of carbene ion, is directly proportional to minus I effect, inversely proportional to plus I effect. Directly proportional to minus I effect, inversely proportional to plus I effect. Okay. Example, molecule, A molecule is tertiary carbene ion. B molecule secondary carbene ion. C species is primary carbene ion taking ethyl group. D species is methyl carbene ion. Now tell me which one stable. So here methyl groups are plus I groups. Methyl group is what? Plus I group. Plus I effect decreases stability of carbene ion. Both are inverse proportional. Plus I groups. What is other name? Electron donating groups. What is other name? Electron releasing groups. Decreases stability of carbene ion. Okay, here electron density is more on this carbon. And these groups also pushing electron towards carbon. Then this become more negative. More negative means less reactive. Here 2 methyl groups pushing electron towards this carbon magnitude of negative charge increases. Here only 1 methyl group pushing electron towards carbon, then electron density of carbon increases. Here hydrogen is neutral. So electron releasing groups decrease stability. Here 3 plus I effects less stable, 2 plus I effects more stable, only 1 plus I effect more stable, no plus I effect more stable. That's why stability among A, B, C, D, which one is more stable? D more stable than, C more stable than, B more stable than A. Okay. So next, if you see stability of some more carbene ions, how minus I groups affect stability of carbon ion. We know minus I groups increases stability of carbon ions. Minus I groups are also called as electron withdrawing groups. Minus I groups are also called as electron withdrawing groups. Electron withdrawing groups. Electron withdrawing groups. Minus I groups are also known as electron withdrawing groups. Okay, right. Taking one more example. If I write formic acid, this point I will write later. Okay, formic acid and acetic acid. Between formic acid and acetic acid, electron withdrawing group increases. Same point. Electron withdrawing groups, minus I groups. Minus I groups are also called as electron withdrawing groups. Electron withdrawing groups. Electron withdrawing groups. Taking carbon ion. This is A molecule. B molecule is CH2, Cl. C species, not molecule, ion. C ion is here bromine, and D ion, except electron withdrawing group, remaining all is same. Now tell me stability of carbon ion. Fluorine, chlorine, bromine and iodine are. Fluorine, chlorine, bromine and iodine are. Fluorine, chlorine, bromine and iodine are minus I groups. Their minus I effect order. Fluorine, chlorine, bromine and iodine. Which one is strong electron withdrawing group? Which one is minus I group? Fluorine. You know minus I groups increases stability of carbon ion. Between A, B, C, D, A is more stable. Stability order. Stability of carbon ion follow this order, because carbon ions are stabilized by minus I group. Fluorine strong minus I group compared to chlorine. Chlorine strong minus I group compared to bromine. Bromine strong than I. Next example. CH2 minus CH2 NO2. This is A molecule, B molecule, CH2. Here I am writing fluoro, CH2 OH. Your order is A, B, C. NO2 strong minus I group than fluoro strong, fluorine strong electron withdrawing group than OH. That's why order like this. Take this one. Next, third example, CH2 CHF CH2 CH3. B species CH2 CHF CH3. C species CH2 CH2F. Which one is more stable? We know fluorine is electron withdrawing group, minus I group, that increases stability of carbon ion. This is stable. Here also fluorine. Here also fluorine. In all these three cases, fluorine is present, that is minus I group, that increases stability of carbon ion. Here, C distance. As the distance increases, inductive effect decreases. So here minus I effect more, here minus I effect less, here minus I effect very less. As minus I effect decreases, stability of carbon ion also decreases. So order is A, B, C. So which is more stable? A more stable than B, more stable than C. Okay. Next, third application. Stability of, it explains stability of carbon free radical. It explains, third application, it explain stability of inductive effect, explain stability of carbon free radical. Carbocation stability, carbon ion stability. Here carbon free radical stability. So note this point here. Carbon free radical stability resembles with carbocation stability. Carbon free radical stability similar to carbocation stability. What does it mean? Stability of carbon free radical directly proportional to which effect? Plus I effect, similar to carbocation stability. Inversely proportional to which effect? Minus I effect. Example, alkyl groups. Any alkyl group, I am taking simply methyl group. Tertiary carbon free radical. Next, taking secondary carbon free radical. Next, taking primary carbon free radical. Next, methyl carbon free radical, that is super primary. Methyl carbon free radical. Stability order, if it is A, B, this is C and this is D. Stability order, which one is more stable? A more stable than, B more stable than, C more stable than D. A more stable than, B more stable than, C more stable than D. Thus, carbocation, carbon ion, carbon free radical stability explained by inductive effect. Take this one. Next, fourth one, this is important one. Acidic strength of organic acids explained by inductive effect. So how it will be? Suppose HA is some acid. First of all, we need to remember organic acids are weak acids compared to inorganic acid, perchloric acid, sulfuric acid, nitric acid. Those are inorganic acid. Organic acids are weak acids. Organic acids are weak acids. So taking HA, that split into A minus and H plus. So here HA is a species that provide H plus ion. In Bronsted sense, it is what? Acid. A minus is conjugate base of HA acid, conjugate base, shortly CB. Here what is CB? Conjugate base, that is anion. Here conjugate base, here since CB, conjugate base is an anion, since conjugate base is anion, its stability can be explained by I effect. Anion stability explained by I effect. So the acids whose conjugate bases are stable are said to be strong acid. If conjugate base is stable, corresponding acid is strong acid. If conjugate base is unstable, corresponding acid is weak acid. So what is the point? If conjugate base is stable, corresponding acid is, its acid is strong. If conjugate base is stable, its corresponding acid is strong. If conjugate base is unstable, corresponding acid is weak. Corresponding acid is weak. If conjugate base is stable, corresponding acid is strong. If conjugate base is weak, corresponding acid is weak. That means acid strength depends on stability of conjugate base. If conjugate base is stable, corresponding acid is strong. If conjugate base is unstable, corresponding acid is weak. That means the acidic strength of acids depends on stability of conjugate bases. Stability of conjugate bases can be explained by inductive effect. Okay, so since what is order anion stability to inductive effect? Stability of conjugate base is directly proportional to, since it is anion, directly proportional to minus I effect, inversely proportional to plus I effect. What does it mean? Stability directly proportional to, stability of conjugate base proportional to acidic strength. Therefore acidic strength of organic acid, acidic strength directly proportional to what? Stability of conjugate base, stability of conjugate base. Stability of conjugate base directly proportional to minus I effect, inversely proportional to plus I effect. This is the relation, important relation. Strength of organic acid directly proportional to minus I effect, inversely proportional to plus I effect. In general, acidic strength of acid depends on its stability of conjugate base. Conjugate base stability explained by inductive effect. Since conjugate base is anion, its stability can be explained by inductive effect. That means stability of conjugate base explained by inductive effect. Stability of conjugate base decide acidic strength. That means acidic strength explained by inductive effect. Okay, right, take this one. Sometimes questions they may ask like this: write Ka order of following acids or pKa order of following acids. They may ask Ka order, acid dissociation constant order, and pKa orders also. In such times, HA is acid, that gives what? A minus ion conjugate base plus H plus ion. Acid dissociation constant, acid dissociation constant Ka is equal to, what is acid dissociation constant? That is equilibrium constant, your equilibrium between dissociated and undissociated species. Because this is weak electrolyte. For weak electrolyte there is an equilibrium between dissociated and undissociated. So Ka is equal to product of molar concentration of product by product of molar concentration of reactant. From the above, what we can say? As Ka value increases, molar concentration of H plus increases. If Ka increases, what happens? Molar concentration of H plus ion increases. As molar concentration of H plus increases, acidic strength increases. Acidic strength increases mean proportionality. Therefore, acidic strength of acid, acidic strength directly proportional to what? Ka value. Acidic strength directly proportional to what? Ka value. This is one relation. Other is, we know pKa is equal to minus log Ka, pH is equal to minus log H, pOH is equal to minus log H, OH, pK is equal to minus log Ka, pKb is equal to minus log Kb, pKw is equal to minus log Kw. That means as pKw increases, as pKa increases, as pK increases, this is negative, numerator but negative. That means Ka value decreases. As Ka value decreases, what happens? Acidic strength decreases. Acidic strength decreases. From that, what we can write? pKa increases, acidic strength decreases. Therefore, acidic strength or acidity, inversely proportional to what? pKa value. Acidic strength directly proportional to Ka value, acidic strength inversely proportional to pKa value. Okay, take this one. Okay, application example. Between tertiary butyl alcohol or among tertiary butyl alcohol, isopropyl alcohol, ethyl alcohol and methyl alcohol or methanol. Which one is strong acid? So order is acidic strength order, acidity order. Why? Because so their acid's stability explained by conjugate bases. Conjugate bases CH3, here CH3, O minus. In second case, their conjugate bases, next one ethoxide and methoxide. Which one is stable? Anions stability, inductive effect, these are plus I groups. Anion stability, inverse proportional. So these electrons push bond pair towards oxygen, then magnitude of negative charge on oxygen increases. When negative charge increases, stability decreases. Here 2 plus I groups. Here only one side. Here small plus I group. Which one is more stable? This is more stable. Here magnitude of negative charge is less. Here 2 electron donating groups. Here both sides electron donating group. Here all 3 sides electron donating group. Stability of CB's conjugate bases increases. I will write second. If you compare formic acid and acetic acid, so which one is strong acid? Definitely A strong acid than B, because this is neutral and this is what? Plus I group. Plus I groups decreases acidic strength. Minus I group increases acidic. Minus I groups increases acidic strength. Plus I group decreases acidic strength. Plus I groups decreases acidic strength. Plus I group push electron towards anion, then magnitude of negative charge on anion increases, its reactivity increases, but stability decreases. Okay, take this one. Next example. Acetic acid, CH3COOH. Acetic acid. Chloroacetic acid, second option. Dichloroacetic acid. trichloroacetic acid, increasing order of acidic strength or decreasing order of acidic strength, right, in which Cl group is minus I group. Minus I groups increases acidic strength of acids. Here 2 minus I groups, here 3 minus I groups, here 2 minus I groups, here 3 minus I groups. Therefore, acidic strength A, B, C, D, this order. Next one, if we see trichloroacetic acid and difluoroacetic acid, next triiodoacetic acid. Among these three, we know that chlorine is minus I, 3 minus I groups. Here only 2 minus I groups, 2 minus I groups, here 3 minus I groups. Between chloro and iodo, chloro is strong minus I group, and this is weak minus I group. It is very strong minus I group, but those are 2 in number. That's why definitely A is stronger, B is weaker than C, C is weaker than A. This is the order. Next, if we see formic acid, HCOOH, and 2 acetic acid, formic acid, acetic acid, and benzoic acid, D, iodoacetic acid. Between these three, formic acid stronger acid than benzoic acid, stronger acid than acetic acid, but here some minus I group is there. That's why D stronger than, A stronger than, C stronger than, next what? B. This is the order. So I will give one order: relative strength of acidic nature, relative strength of acidity of organic acids. So among organic acids, benzene sulfonic acid is stronger acid than formic acid, which is stronger acid than benzoic acid, which is stronger acid than acetic acid, which is stronger acid than carbonic acid, H2CO3, which is stronger acid than what? Phenol, which is stronger acid than water. Water is even stronger than alcohol, okay, stronger than ammonia, stronger than benzene, stronger than what? After alcohol, acetylene stronger acid than ammonia, stronger acid than benzene, stronger acid than ethylene. Acidity order. So order is like this, but here only one difference between alcohol and water, between alcohol and ether, alcohol and water, methanol is stronger acid than water. Water is stronger acid than any other alcohol. What is R here? R is other than methyl group, other than CH3 group, other than methyl group. Note this one. So this is the order we need to remember. Comparison of acidity of organic acids is important in competitive. Okay, right. Next, if I give one order, if I give this order, formic acid, B acetic acid, C phenol, D benzoic acid. So by looking at this one, we can easily say first formic acid is stronger acid than benzoic acid, stronger acid than benzoic acid is D option. Between acetic acid and phenol, acetic acid is stronger acid. B stronger acid than C. Okay. So that by following this order we can answer easily. And moreover, it is important to remember minus I groups increases acidic nature of organic acids. Next example, last example important. Between CH4 and NH3, H2O and HF, acidic strength follows A less than B less than C less than D, because based on strength of stability of their conjugate bases. If we see conjugate bases of above acids, region stability CH3 minus NH2 minus OH minus and F minus, stability order follows like this, because more electronegative, note point, more electronegative atom with negative charge, more electronegative atom with negative charge, more stable compared to less electronegative atom. More electronegative atom with negative charge is more stable. Okay, so this is about inductive effect.